concept of independence is an important one in probability theory. It's also a slightly subtle concept, so in this lesson we're going to work through some examples, and hopefully by the end of the lesson you will have a clearer idea of what independence means in the context of probability theory. First, let's write down an intuitive idea of what independence is. So intuitively, we might say that two events are independent if they have no effect on each other. Now, this is not a very mathematical statement, but I think it captures the intuition of what independence means. Let's look at an example. So here are two events that most people would agree are independent. The first one is the event, it will rain tomorrow in Beijing. And the second event is, I will win the lottery next year. It's fairly clear that these two events have no effect on each other, and intuitively we would say that these two events are independent. Let's consider another example. So here are two events that are clearly not independent. The first one is Kerry win next year's All-Ireland Football Championship, and the second one is Dublin win next year's All-Ireland Football Championship. Clearly, these events affect each other. If Kerry win the championship, then Dublin cannot, and vice versa. So clearly these events are not independent, according to our intuitive idea. Okay, so that's the intuitive idea of independence. However, our intuitive idea is not very easily translated into mathematics. It is hard to say precisely what we mean by saying events have no effect on each other. So in order to address this problem, we need a more mathematical concept of independence, and probability theory provides us with this precise notion of independence. So let's write down what we mean by independent events in probability theory. So here's what we mean by independence in probability theory. And it looks a bit more complicated, so we'll spend some time trying to understand this. So we say that A and B are independent events if the probability of A, this thing here on the left of this equation, is the same as the probability of A given that B occurs. So here on the right we're looking at what's the probability of A if we know that the other event occurs, if the other event B occurs. We can work out that probability, and if that turns out to be the same as the probability of A without knowing anything about B, and also if the probability of B is equal to the probability of B given that A occurs, then we say that these two events are independent. So another way of thinking about these equations is that what this is saying is that the probability of one event is unaffected by whether or not the other event occurs. The probability of A is the same whether or not B occurs. And the probability of B is the same whether or not A occurs. Okay, so that definition is a little bit tricky, so let's try and illustrate this with some examples. So let's say that we roll two dice, and we'll suppose that the dice are colored red and blue, just so we can distinguish them. And now let's look at two events. So let's say that event A is that the red die shows a 6, and event B is that the blue die shows a 3. Now it's clear that the result of one die has no effect on the result of the other die. So the probability of the red die showing a 6 is not affected at all by what the blue die shows. And the probability of the blue die showing a 3 is not affected at all by what the red die shows. So these two events are independent. The probability of event A, that is the red die showing a 6, is 1 over 6. And that's the same as the probability of A that B occurs. Given that the blue die shows a 3, the probability that the red die shows a 6 is still 1 over 6. And the same goes the other way. The probability of B, the probability that the blue die shows a 3, is also 1 over 6. And that's the same as the probability of B given that A occurs. No matter what the red die shows, the probability that the blue die shows a 3 is always going to be 1 over 6. So these two events are independent events. Let's look at another example now. So here's another example involving a die. But now we're just going to roll a single die, and we're going to look at the two events described here. So event A is the event that an even number comes up, and event B is the event that either 1 or 2 comes up. And again, we ask this question, are these events independent? So now our intuition maybe is not so helpful. In the previous example, where we had two separate dice, it was fairly clear that the results of the two individual dice were independent. But now it's not so clear. So let's see if we can use our definition to establish whether or not these two events are independent. So first of all, let's work out the probability of A. What's the probability that an even number comes up? We have looked at examples like this in previous lessons. So the probability of an even number is the number of successful outcomes. So how many even numbers are there? 2, 4, or 6. So there are 3 of them, divided by the total number of possible outcomes, which is 6. So it's a half. And what about the probability of event B? What's the probability that either a 1 or a 2 comes up? Well, again, the number of successful outcomes in this case is 2, and the total number of outcomes is 6. So 2 over 6, which is 1 over 3. So now to consider the independence of these events, we have to look at the probability of an even number given that 1 or 2 comes up, and the probability of 1 or 2 given that an even number comes up. So let's look at the probability of an even number given that 1 or 2 comes up first. So what is this probability? Well, the sample space is just 1 and 2. So given that 1 or 2 comes up, those are the possible outcomes. So the sample space is the set consisting of 1 and 2. And these are equally likely. And how many of them are even? Well, one of them is. So there's one successful outcome out of 2 possible outcomes. So the probability of an even number, given that 1 or 2 comes up, is a half. And we compare with the probability of an even number, and we see that they're the same. So that's good. It passes the first test. So let's do the same for the probability of 1 or 2, given that an even number comes up. So what's the sample space in this situation? What are the possible outcomes given that an even number comes up? Well, if an even number comes up, then the sample space must be the set consisting of 2, 4, and 6. And these are all equally likely. And the only successful outcome is 2, because we're looking for a 1 or a 2, and 2 is the only one that occurs in the sample space. So the probability of a 1 or a 2 given that an even number comes up is 1 over 3, because there's one successful outcome in the sample space and 3 total outcomes, and they're equally likely. And again, we compare with the probability that a 1 or 2 comes up, and we see that that was also 1 over 3. So we've checked the conditions here, and we find that these two events are actually independent. So this is a good example to think about, because our intuition may not tell us whether or not these two events are independent. However, by calculating the probabilities as shown here, we can establish that these two events are in fact independent of each other.